Next, the F-104. We consider that the cost and performance of that model excellent, and I guess after some 2,500 of them having been built around the world, we consider the F-104 series a success. The story of the F-104 began during the Korean War. Kelly Johnson visited frontline squadrons in 1952 to determine what characteristics the next generation of U.S. Air Force fighter planes should possess. At that time, the Republic F-84 Thunderjet and North American F-86 Sabre were being outperformed by the Soviet-built Mikoyan-Gurevich MiG-15, particularly at high altitudes. Predictably, the reaction of the pilots was a demand for greater speed, altitude, and rate of climb, even at the expense of maneuverability, armament, range, ease of maintenance, and creature comforts. Johnson returned to Lockheed with the notion of a lightweight, fast-climbing, high-speed, high-altitude, daylight interceptor. The idea was not exactly a new one, but in pursuing it, Johnson was leading Lockheed onto financially risky ground. The concept of the specialized interceptor had been explored from time to time since World War I, and it had usually been discredited. The problem lay in the interceptor's lack of operational flexibility. No one wanted a combat plane that performed one mission well to the exclusion of all other missions. Johnson was convinced, however, that he and his staff could produce such a quantum leap in aircraft performance that the Air Force would have to take notice. If one could describe the airplane that Kelly Johnson and his team designed in 1952, it would be extreme. The Model 83, as the F-104 was originally known, was created for the sole purpose of flying faster and higher than any other fighter in the world. It was, in essence, the smallest fuselage and wings that could be constructed around the most powerful available engine, one pilot, and the minimum necessary fuel and armament. The F-104's maximum airspeed of Mach 2.2 was dictated primarily by shock wave propagation in the air intakes, by the thermal limitations of the aluminum alloy from which the airframe was constructed, and the amount of stress that the canopy attachment points could take. Air pressure could pull it from the cockpit at speeds above Mach 2.2. To handle temperatures generated at higher speeds, the airframe would have had to have been built of titanium, rendering it far too expensive for mass production. The F-104 was the first aircraft to be powered by the then new 14,800-pound thrust General Electric J-79, an engine that was to set a new standard for power-to-weight ratio. The jet engine air intakes on the F-104 were fitted with movable semicircular shock cones designed to adjust the airflow at various speeds. Such devices became commonplace on jet planes in later years, but were unheard of prior to the F-104. The shock cones were considered so secret that the engine air intakes were completely hidden under aluminum fairings when the Starfighter was first exhibited to the public on April 17, 1956. The engine was not the only revolutionary component in the F-104. The plane's principal armament of a single 20mm cannon may have seemed puny, but it was a very special gun. The Starfighter was the first aircraft designed to use the General Electric M61 Vulcan cannon, a 6-barreled electrically operated Gatling-type gun that could fire an unprecedented 6,000 rounds per minute, a rate of fire that could use up the F-104's complement of 725 rounds in just over 7 seconds. The Air Force was understandably dubious about the effectiveness of a gun fired from an airplane that was flying as fast as a bullet. Its operational requirement therefore stipulated that the F-104's armament should be augmented with yet another new weapon system, the heat-seeking AIM-7 Sidewinder air-to-air missile. A single Sidewinder was mounted on a rail on each wingtip. The Starfighter's T-shaped tail was also unprecedented. The configuration was arrived at after evaluating no less than 285 different designs. By far, the most astonishing feature of the Starfighter was its wings. In an era of swept wings and broad delta wings, Lockheed broke with convention by giving the F-104 tapered wings of low aspect ratio that were remarkably small. Unlike most aircraft designs, the F-104's wing format was chosen solely for efficiency at supersonic speed, without any consideration for lift, maneuverability, or ease of handling at lower speeds. To compensate, the entire leading edges of the wings were designed to pivot downward to increase lift for takeoff and landing. Lift was also augmented by ingenious trailing edge flaps that had high-pressure air vented from the engine blown across their upper surfaces. With a thickness at the wing root of 4.2 inches, a great deal of design ingenuity was necessary to develop aileron and flap actuators small enough to fit inside them. The edges were so sharp that special covers had to be installed over them to prevent ground crewmen from injuring themselves. Another unusual feature of the F-104's wings that was not obvious from the outside was that they were not connected to each other by a continuous main spar, but by a frame encircling the fuselage. There were penalties to be paid for the Starfighter's speed. The tiny thin wings that endowed the F-104 with its high performance also gave it a blistering stall speed of 198 miles per hour. To help stop the Starfighter, Lockheed gave it a powerful drag chute. It also had a tailhook, similar to those found on carrier-based fighters, but an unusual feature on a land-based fighter. Since the wings could accommodate neither fuel tanks nor landing gear, both had to share the limited space available inside the narrow fuselage. As a result, the F-104 was never to be noted for its endurance, even with extra fuel tanks fitted to the wingtips. The F-104's design also gave it a high wing loading, which rendered its maneuverability less than ideal, particularly at subsonic speeds. In the 1950s, however, it was generally believed that high-G subsonic dogfighting would no longer be a decisive factor in future air battles, which would be fought at high altitudes by supersonic fighter planes armed with guided missiles, aircraft such as the Starfighter. That supposition would be rudely contradicted in the coming decades over Vietnam, the Middle East, and the Indian subcontinent. Lockheed test pilot Tony Levier flew the prototype XF-104 for the first time on March 4, 1954. The airframe was ready before the J-79 engine, so the XF-104 was first flown with a Wright XJ-65W6 engine. Even though the J-65 only produced 10,200 pounds of thrust, 31% less than the J-79, the XF-104 attained a speed of Mach 1.79 on March 25, 1955, becoming the first fighter to exceed 1,000 miles per hour. The XF-104 was eventually succeeded by 17 service test YF-104As with J-79 engines. Kelly Johnson's faith in the Starfighter concept was vindicated when the YF-104A became the first aircraft type to set both speed and altitude records. Major Howard Johnson climbed to an altitude of 91,249 feet on May 7, 1958, and 4 days later, Captain Walter Irwin attained a speed of 1,404.19 miles per hour. The aircraft also demonstrated an incredible climb rate of more than 60,000 feet per minute. The Starfighter's altitude performance was so impressive that Lockheed later built 3 NF-104As equipped with auxiliary rocket engines and reaction jet controls, like those on a spacecraft, for operation at altitudes so high that conventional controls were no longer effective. Apart from everything else, the F-104 was one of the most exciting-looking aircraft in the world in the mid-1950s, The Starfighter combined unparalleled performance with an appearance that was both extraordinarily beautiful and wholly original. The U.S. Air Force ordered 155 production F-104As in 1955, a number that was raised to 722 in 1958. So many problems remained to be ironed out, however, that the first 35 fighters were diverted to the flight test program. In 7 years, 49 of the 153 that were eventually built were lost to accidents, a staggering 32%. 18 pilots were killed during the same period. In addition, operational experience with the F-104A was raising questions about its limited armament, range, maneuverability, and versatility. Lockheed responded to criticism of the F-104A with a more versatile fighter-bomber version. Designated the F-104C, the improved Starfighter's once pristine lines were cluttered up with external hardpoints for up to 4,000 pounds of bombs, missiles, and fuel tanks. F-104Cs were used in Vietnam by the 435th, 436th, and 476th Squadrons of the 479th Tactical Fighter Wing, TFW, from 1965 to 1968, but Vietnam was not really a suitable venue for them. Since there was nothing for them to intercept, there was no opportunity for the Starfighter to be used to its best advantage. The F-104C also demonstrated that it was still as dangerous to its own pilots as the enemy was. The 435th Tactical Fighter Squadron lost 5 Starfighters to enemy action in Vietnam, but lost another 6 in accidents. In 1958, West Germany, whose Luftwaffe had been resurrected 2 years earlier, was in the market for a supersonic multi-role fighter. They wanted an aircraft able to perform air defense, reconnaissance, interdiction, close support, maritime strike, and even nuclear bombing missions. Despite the fact that the Starfighter had been originally designed as a specialized interceptor, Lockheed managed to adapt it to meet all the Germans' requirements as the F-104G. It incorporated a redesigned airframe, a more powerful version of the J-79 engine, a larger tail, an inertial navigation system, improved radar, and 5 hardpoints for external stores. Over the course of the next 2 decades, it became one of the most widely used fighter types in the world. In NATO alone, Starfighters served in the air forces of Canada, Norway, Denmark, West Germany, the Netherlands, Belgium, Italy, Spain, Turkey, and Greece. West Germany, the largest user, acquired more than 600 of them. The F-104G became, for all intents and purposes, the first Eurofighter. In addition, a further 238 F-104Gs were manufactured in Canada by Canada Air as CF-104s. A total of 1,585 F-104Gs and CF-104s were built, including 2 seat conversion trainers. That was more than 5 times the number of Starfighters built for the U.S. Air Force. The last production version of the Starfighter was the F-104S, an all-weather interceptor developed by Italy in 1968. Air Italia produced 205 F-104Ss for the Italian Air Force, plus an additional 40 for the Turkish Air Force. The last F-104S was completed in 1979, a quarter of a century after the flight of the first Starfighter. Lockheed offered one final development of the F-104 in the late 1960s. Called the CL-1200 Lancer, it differed from the Starfighter in having a longer fuselage, carrying more fuel, a larger shoulder-mounted wing, and a conventional low-set tailplane. The Lancer came along too late to gain acceptance and never got beyond the mock-up stage. The F-104 was the product of a period when air combat was expected to be waged at ever higher speeds and altitudes. Whatever faults the aircraft had are directly traceable to the early 1950s philosophy. By the time the Starfighter became operational, that trend had begun to reverse itself. Today, air combat is often carried on just above the ground, considering the fact that it had originally been intended as a specialized interceptor of high-flying bombers. Lockheed did a remarkably good job of adapting the F-104 into a multi-role Eurofighter. The F-104 deserves a place in the pantheon of American aviation achievements as the first combat aircraft to fly at double the speed of sound. It also deserves recognition for the part it played in NATO's air defense during the Cold War and for its role in resurrecting the European aerospace industry. Kelly Johnson, in summarizing the F-104 in a paper released on June 18, 1957, presciently noted, "It is very difficult to see where added high speed is worthwhile, and it appears that the development of armament, radar, and fire control systems is the most fruitful field to our research efforts over the next 5 years. Above all, it deserves to be remembered as the breathtaking missile with a man in it." The U-2s, we underran our contract on that and gave back the government over 20% of the first contract. It was a success. It was the first time when the Skunk Works went into production. Because of security and other reasons, we, for the first time, made more than 2 of anything, and we made the complete line of the U-2s and the other versions that have come from it. High-altitude strategic reconnaissance philosophy was first articulated during late 1952, when an Air Force major by the name of John Seaberg placed on paper ideas he had for achieving sustained flight at ultra-high altitudes. Seaberg had noted the new generation of turbojet engines could be mated to an aircraft with an extremely efficient high-aspect ratio wing and achieve cruising altitudes far in excess of any aircraft then in service. On May 18, 1954, some 2 weeks after returning from Washington, D.C., a new proposal for a high-altitude cruise aircraft from Lockheed's preliminary design organization arrived on Seaberg's desk for review. Johnson's own insights into the beginning of the aircraft are only thinly recounted in his U-2 log. December 1953. We started an investigation of wing area modifications and stripping procedures to modify the F-104 airplane to get the maximum possible altitude for reconnaissance purposes. Seaberg and his fellow right field engineers spent 3 weeks evaluating the Johnson proposal.
In the early 1950s, the United States had a real requirement to overfly Russia to find out the status of their development of long-range missiles. There was no airplane in the United States or in the world that could safely overfly Russia at that time. Lockheed made an unsolicited proposal to Trevor Gardner, the Undersecretary for Research and Development for the Air Force, on a very specialized airplane. We promised to build within 8 months 20 airplanes for $22 million, including spares, that would do the job required. The program was turned over to the CIA, who then chose Mr. Richard Bissell, an economist, to run the program. Richard Bissell became a very good engineer, and he not only was our director on the U-2 program, but he also followed through with the development of the Mach 3 Blackbird.
When I first met Kelly, I had been working for nearly a year for Allen Dulles. I joined Allen's organization early in 1954. Toward the end of November, I was summoned one afternoon into Allen's office, and I was told, with absolutely no prior warning or knowledge, that one day previously, President Eisenhower had approved a project involving the development of an extremely high-altitude aircraft to be used for surveillance and intelligence collection over denied areas in Europe, Russia, and elsewhere. We had, on the basis of Kelly's proposal, an almost impossible schedule to meet. It was almost impossible for Lockheed, but I can assure you that it was also an extremely tight schedule working within the bureaucracy.
Given the temporary design number CL-282, it consisted of a slightly modified XF-104 fuselage and associated vertical and horizontal tail surfaces. Most noticeable, however, was the deletion of the XF-104's distinctive trapezoidal-shaped wings, and their replacement by a high aspect ratio wing of extraordinary span. Designed into the latter were 4 integral fuel tanks complemented by a 5th tank in the fuselage. Together, these provided a total fuel capacity of 925 gallons. After a thorough but rushed review, Seeberg and his staff rejected the CL-282. Johnson, after receiving word of the negative report, would note, June 7, 1954, received a letter which turned down our proposal on the basis that it was too unusual, that it was a single-engine aircraft, and that they were already committed to the Martin program. When the Air Force informed Johnson of its decision to eliminate the CL-282 from contention, Johnson decided to pursue funding through other channels. Johnson's timing could not have been better. Numerous sources had begun to input data into the U.S. intelligence community indicating the Soviet Union was moving ahead quickly with an extensive family of liquid-fuel, nuclear warhead-equipped intercontinental ballistic missiles. On November 19, 1954, Johnson would make the following log entry. I met with the Government Advisory Board. They wanted to be reassured that our proposal was technically feasible. They believed my story that we could make such an airplane in the time mentioned, and also asked why Lockheed seemed to be the only one who could do this job. General Putt answered graciously that we had proven it 3 times. As it turned out, this was a momentous decision. In one master stroke, Johnson, with Gross's blessing, had transformed the virtually non-existent Skunk Works into not only a full-scale advanced design and engineering team, but a production facility as well. Secrecy had mandated the change. Eisenhower had agreed the funding and direction of the project, to be codenamed Aquatone, would be through the offices of the CIA rather than the Air Force, with Richard Bissell to direct. Earlier on November 9, 1954, Trevor Gardner had visited with Lockheed President Robert Gross and Johnson at Lockheed's Burbank facility. Following a review of the full-scale U-2 mock-up, Gardner gave official confirmation of project approval and a directive to go ahead with prototype construction. Johnson promised the first Aquatone aircraft would be in the air no less than 8 months after the first metal was cut. On December 10th, the design was frozen, and on December 20th, Johnson noted in his log, "Working like mad on airplane. Initial tunnel tests successful." Among the unique weight-related accomplishments of the design program were the following. Wing weight was kept to an almost unbelievable 4 pounds per square foot. The landing gear was a bicycle arrangement with the heaviest component consisting of a single main strut. The tail assembly was attached at the center fuselage by only 3 bolts. The side-opening canopy was manually operated. The control system was unboosted. Hydraulically actuated systems were kept to a minimum. There was no cockpit pressurization, and there was no ejection seat. On the morning of August 4, 1955, Johnson, Ernie Joyner, Glenn Fulkerson, Bob Murphy, and several other Skunk Works personnel watched as Levier climbed into Article 341 in preparation for its first real flight. Given the call sign Angel 1, the aircraft was to be chased by a company-operated C-47, with Johnson and test pilot Bob Matty as observers. Customers also had been brought in from Washington, D.C., and they arrived at the test location by transport just prior to Levier's takeoff. Levier recalls the first takeoff and climb, taking place at 3:55 p.m., went perfectly, and that he encountered no problems or difficulties during the ascent. Leveling at 8,000 feet, he spent 45 minutes cycling the landing gear, deploying and retracting the flaps, exploring stability and control characteristics, checking engine temperatures and exhaust pressure ratios, and practicing power-off stalls. There were no malfunctions of any kind. Lougheed completed a total of 20 flights in the Angel before being transferred back to the F-104 and other Lockheed flight test programs on September 1st. Additionally, Lougheed became the first pilot to take the aircraft to 50,000 feet. The latter required the use of a partial pressure suit. This had forced Lougheed to go through the Air Force's high-altitude training program. When he completed the curriculum at the age of 42, he was at the time the oldest pilot to do so. During this initial flight test period, the Air Force, at Johnson's recommendation, assigned the innocuous U-2 designator to the aircraft as its formal military alias. The flight test program during the remaining months of 1955 progressed smoothly. December 1st marked the U-2's first-year anniversary, which Johnson duly noted. "We have built 4 flying airplanes, have the 9th airplane in the jig, and have flown over our design altitude any number of times. We've trained crews and are developing the Bakersfield factory. It's been quite a year." On June 19, 1956, CIA pilot Carl Overstreet departed Wiesbaden on the first operational flight. After overflying Warsaw, Poland, and returning via Berlin and Potsdam, he landed without incident and delivered to the U.S. intelligence community the first ever surreptitiously taken U-2 photos. The results were spectacular. The quality of the imagery generated by the Type B folded optics camera was everything the CIA had hoped for. Resolution, contrast, and quality were far beyond anything previously seen. Baker, at Harvard University, and an astronomer by training, was one of the leading lens designers in the U.S. during the 1940s and 1950s. By now, Soviet diplomatic circles were impacted. The U-2 flights had been tracked with little difficulty by Russian radar, and the Soviet government was embarrassed by the ease with which the aircraft were able to penetrate Russian airspace. The military repercussions were great. In a communique dated July 10, 1956, the Soviet ambassador to the U.S. in Washington was asked to deliver a formal protest to the U.S. government and request that the overflights cease. In responding, U.S. diplomats denied that any military aircraft had been involved in such activity. This was, of course, true, as the CIA was a civilian and not a military agency. During 1958, the Soviets began to gather momentum in their efforts to develop an effective U-2 countermeasure. The SA-2, an improved surface-to-air missile, eventually codenamed Guideline by the West and equipped with a warhead that had a kill pattern with a diameter of about 400 feet, was pushed into service and for the first time threatened the U-2's high-altitude dominance. Though the estimated 2% probability of kill was low, for the first time the U-2 was forced into taking the new SA-2 launch sites into consideration. By the end of its 3rd year of operation, the U-2's intelligence-gathering ability had become the single most important tool in the entire U.S. intelligence community arsenal. CIA U-2 operations were not confined to the Soviet Union during this period. During late September of 1956, Gary Powers flew across the eastern Mediterranean and gathered intelligence data on the positions of British and French warships as they prepared to aid the forthcoming Israeli invasion of Egypt.
CIA, I had heard of it before this. I knew what its purpose was. I knew what they did, but they were a very little known organization at that time, and I probably knew as much or as little as anyone else. I knew hardly anything about it except that I knew it was a highly secret intelligence gathering organization. They had this plan with a new plane to do espionage over the Soviet Union. I knew that flying this airplane without permission over the Soviet Union was spying. I knew that it was. But I really don't think that, in the true sense of the word spy, that I ever considered myself a spy. I was a pilot flying an airplane, and it just so happened that where I was flying made what I was doing spying. I felt that it was a very necessary thing, and I was very proud of my country for having, I guess the word is the guts to do this, because I had felt, and a lot of people had felt, that we had not been responding the way that we should have responded to threats from the communist nations such as Korea and so forth. When I found out that they were, I was very proud.
Further flights followed during the Suez Crisis and later, during crises involving Syria, Iraq, Saudi Arabia, Lebanon, and Yemen, all to gather intelligence data on military activities and the eternal warring between these various Middle Eastern countries. Additionally, U-2 overflights over the Xinjiang and Jiangxi provinces in China began on December 6, 1958. On May 1, 1960, the U-2 was thrust into the public spotlight when one flown by Francis Gary Powers was shot down over Sverdlovsk by a surface-to-air missile.
An unarmed plane, a U-2 weather research plane based at Adana, Turkey, piloted by a civilian, has been missing since May 1. During the flight of this plane, the pilot reported difficulty with his oxygen equipment. Mr. Khrushchev has announced that a U.S. plane has been shot down over the USSR on that date. It may be that this was the missing plane. It is entirely possible that having a failure in the oxygen equipment, which could result in the pilot losing consciousness, the plane continued on automatic pilot for a considerable distance and accidentally violated Soviet airspace. The United States is taking this matter up with the Soviet government with particular reference to the fate of the pilot.
Captured, Powers became the center of the resulting U-2 incident, which embarrassed Eisenhower and effectively ended a summit meeting in Paris.
I shall bring up the open skies proposal again at Paris, since it is a means of ending concealment and suspicion. My final point is that we must not be distracted from the real issues of the day by what is an incident or a symptom of the world situation today. This incident has been given a great propaganda exploitation. The emphasis given to a flight of an unarmed, non-military plane can only reflect a fetish of secrecy.
The incident led to an acceleration of spy satellite technology.
I felt that by talking to them as freely as I could, tell them the absolute truth about everything that they knew about, I could establish a basis of truthfulness. So when it did come to sensitive something that I didn't want to tell them about, I could lie and they would believe me, and this worked fairly well. But there was still this threat of torture, and I felt that if I were tortured, that any information they wanted, I might give. I didn't know how I would react to torture, so that if I could prevent this anyway, then I had to do it, because I had some information that they could have used.
Remaining a key strategic asset, U-2 overflights of Cuba in 1962 provided the photographic evidence that precipitated the Cuban Missile Crisis. On October 22, 1962, President Kennedy made his now famous speech revealing publicly that Cuba had acquired an extensive offensive weapons capability, including MRBMs and IRBMs. In an unquestionably threatening tone, Kennedy declared that any Cuban missile launch would be regarded as an attack by the Soviet Union on the U.S. and that massive retaliatory action would result. He also declared a naval quarantine of Cuba until all Soviet offensive weapons were removed from the island.
It shall be the policy of this nation to regard any nuclear missile launched from Cuba against any nation in the Western Hemisphere as an attack by the Soviet Union on the United States, requiring a full retaliatory response upon the Soviet Union.
During the crisis, a U-2 flown by Major Rudolph Anderson Jr. was shot down by Cuban air defenses. On October 26th, communications with the Soviets indicated they would begin dismantling the Cuban missile sites. On October 28th, this was confirmed. The Cuban Missile Crisis, due in no small part to the photographic intelligence provided by the U-2 surveillance program, had come to an end. Frequent Cuban overflights continued. They still were in progress when President Kennedy remarking, "I must say, gentlemen, that you take excellent pictures." As surface-to-air missile technology improved, efforts were made to improve the aircraft and reduce its radar cross-section. This proved unsuccessful, and work began on a new aircraft for conducting overflights of the Soviet Union. In the early 1960s, engineers also worked to develop aircraft carrier-capable variants, U-2G, to extend its range and flexibility. During the Vietnam War, U-2s were used for high-altitude reconnaissance missions. In 1967, the aircraft was dramatically improved with the introduction of the U-2R. Approximately 40% larger than the original, the U-2R featured under-wing pods and an improved range. The phasing in of the U-2R over Vietnam led to the phasing out of the remaining Air Force U-2Cs. The last of the original U-2Rs was delivered from the Skunk Works Palmdale facility during December of 1968. As Johnson would note in the log, "We are rapidly running out of work on this program." This was joined in 1981 by a tactical reconnaissance version designated TR-1A. The introduction of this model restarted production of the aircraft to meet the U.S. Air Force's needs. The U-2R and TR-1 were critical contributors to Desert Shield and Desert Storm operations. They flew with a variety of sensors for high-resolution photography, radar mapping, and low-light observations. Intelligence agencies, field commanders, the Pentagon, and even the President used this information to identify military targets, estimate enemy troop strengths, and make battle damage assessments. In the early 1990s, the U-2R fleet was upgraded to the U-2S standard, which included improved engines. A production-configured re-engined U-2R completed its qualification phase of flight test at Palmdale during late 1993. 3 U-2Rs incorporating the engine and other upgrades were officially delivered to the Air Force from Palmdale to Beale Air Force Base, California on October 28, 1994. The upgraded aircraft are officially designated U-2S in the single-seat configuration and U-2ST in the two-seat trainer configuration. A total of 37 U-2Rs will be brought up to the new standard by the time the retrofit program ends during 1998. NASA's ER-2s also will be upgraded starting in 1996. Despite its advanced age, the U-2 remains in service due to its ability to perform direct flights to reconnaissance targets on short notice. Though there were efforts to retire the aircraft in 2006, it avoided this fate due to the lack of an aircraft with similar capabilities.
I still think it's one of the best airplanes ever made. It was just a tremendous thrill to be able to look down at the earth far below, and actually early in the mornings, with the sun just coming up, you could see the curvature of the earth out on the horizon, and it's just beautiful. Early in the program, flying this, it was thrilling to know that you were doing something that no one else had ever done, except just very few people who flew this particular airplane. Each flight broke an altitude record.
The JetStar made 2 of them. They were a success as far as the prototypes went. When it was handed over to our Georgia division, here's a case where it wasn't handed over good. It was almost completely redesigned. Went to 4 engines instead of 2. The cost almost killed us in the end, but as far as the prototype part of the program goes, it went well. During the latter part of 1955, It became apparent to the Air Force that its aging and somewhat eclectic utility transport and twin-engine training aircraft fleet was in need of replacement with contemporary hardware. Many of the aircraft then in use for these missions could trace their origins back to the pre-World War II period. All were powered by reciprocating engines. Compounding the Air Force's problem was a post-Korean War funding shortfall that severely restricted new aircraft acquisitions. Nevertheless, the service elected to move ahead with long-term plans under the aegis of the UTX and UCX specifications. In order to do this, it required that the companies submitting proposals also be willing to fund their respective prototypes using their own money. Concurrent with its August 1, 1956 request for proposals, the Air Force made it understood that, if funding constraints were lifted, it would order up to 300 of the winning design. Making the new aircraft doubly enticing for manufacturers was the prospect of corporate and commercial sales beyond those to the military. Kelly Johnson later would note, "With the military as a ready prospect for such a sizable order, we pulled out all the stoppers. We assembled our technical teams, studied the requirements, drew up plans, designed, and built." While the new model CL-329 was conceived, engineered, and flown in less than 8 months, Lockheed had in fact spent some $7 million during the preceding 13 years studying large jet-powered transport aircraft that involved technology advances directly applicable to its forthcoming utility training aircraft. During 1956, the Air Force informed industry there was a military requirement for a small jet transport to meet its UCX and UTX specifications. Johnson and his Skunk Works team, with corporate approval, immediately initiated preliminary design studies based on a small-scale L-193 variant. Accordingly, Johnson decided that in order to get the CL-329 into the air at the earliest possible date, it would be necessary to power it with British-built 4,850-pound thrust Bristol Orpheus 1.5 turbojets. On the morning of Wednesday, September 4th, 1957, the first JetStar taxied out onto the Edwards Air Force Base dry lake bed. At 8:58 a.m., the JetStar became airborne for the first time. It had met Johnson's September 4th first flight deadline and had beaten by 2 minutes the predicted 9 a.m. departure time. Air Force Phase 2 testing was completed during February of 1958 using the first aircraft. It was determined that the JetStar had excellent flight and performance characteristics. On June 17, 1958, the first JetStar embarked on a promotional trip to demonstrate its transcontinental range and high cruising speeds. Unfortunately, though the demonstration tour proved a success, a national recession dictated the Air Force delay its plans to acquire the aircraft for operational services. As a result of the Air Force's intransigence concerning 4 engines versus 2 during January of 1959, Pratt & Whitney J212A turbojets were selected to power the JetStar in its production configuration. On October 31, 1958, the JetStar was picked by the Air Force over North American's NA-246 submission to meet the requirements of the UTX specification, which Lockheed had not originally planned to accommodate. During October, the Air Force announced its plan to acquire the Lockheed aircraft under the designation T-40A. Shortly afterwards, however, it withdrew the initial decision and awarded the contract to North American for what became the T-39A Sabreliner. Eventually, 211 trainer and light transport Sabreliners would be acquired by the Air Force and Navy while Lockheed's JetStar starved for orders. It was not until June of 1960 that an initial Air Force order for 5 JetStars finally arrived. The first of these, by now referred to as C-140A by the Air Force, was delivered during April of 1961. By January of 1962, Lockheed, having spent $100 million on the JetStar program, was facing an $80 million loss. This was attributable to the Air Force's initial indications it would buy some 300 aircraft, when in fact, by mid-January of 1962, it had bought only 16. When JetStar production ended during 1980, with the delivery of the 204th and last aircraft to the Iraqi government, Lockheed had lost a considerable quantity of money, but had learned some very valuable business lessons. The aircraft, regardless of its financial status, proved to be a successful corporate transport. Several versions eventually were built by Lockheed, including the C-140A, the C-140B, and the VC-140B for the military, and the JetStar 6, the JetStar 8, and the JetStar 2 for the corporate market. Then came a number of Mach 3.0 types, the first one of which you'd be familiar would be the YF-12A. Its gross weight is still secret, but the cost performance was excellent. It was a success. Didn't produce any because there wasn't any threat. Not until the backfire bomber showed up. Of the many aircraft whose origins can be traced back to Lockheed's renowned Skunk Works, none is more significant than the A-12. More than any other aircraft, this titanium masterpiece represented the apex of aeronautical engineering in its day, not only at Lockheed, but at every significant aerospace engineering bureau around the world. Today, over 3 decades after its first flight, it remains the aircraft by which all others are judged. Project Suntan had given Kelly Johnson and the Lockheed Advanced Development Team engineers a significant opportunity to explore the attributes of hydrogen propulsion systems. Equally as important, however, Suntan also permitted the exploration of advanced airframes, optimized for the first time to cruise at speeds well in excess of Mach 3. Soon after the U-2's first flight during 1955, Richard Bissell moved quickly to organize the research and development of follow-on systems, including what was to become the A-12. New studies, conducted under the codename Gusto, were initiated exploring the design and possible development of a totally new subsonic reconnaissance platform that would be designed from the start to incorporate the lowest RCS obtainable. The resulting analysis concluded that supersonic speed, coupled with the use of radar-attenuating materials and radar-attenuating design considerations, greatly reduced the chances of radar detection, though it did not reduce it to zero. Lockheed Aircraft Corporation and the Convair Division of General Dynamics during the fall of 1957 were to respond to a general operational requirement calling for a high-speed, high-altitude reconnaissance aircraft, but to do so without a formal contract or government funding. Johnson spent virtually every available minute working on the advanced aircraft program, which he sometimes jokingly referred to as the U-3. Project Gusto now was terminated, and a new codename, Oxcart, was assigned. Ben Rich would note that the A-12 was composed of 85% titanium and 15% composite materials. Learning to work with titanium proved to be a major undertaking. The myriad breakthroughs pioneered by the Skunks Works manufacturing team in conquering this metal remain one of the great and unheralded successes of this most incredible program. Just a great deal of work with the many problems we have trying to get this airplane built. Everywhere you turn, there are tremendous problems requiring invention, new systems, and money. An official first flight, with appropriate government representatives on hand, now was made on April 30th. Nearly a year behind schedule, the aircraft became airborne for the first time. With Lou Schulk at the controls, the aircraft lifted off at 170 knots. The landing gear was retracted, and a climb was made to 30,000 feet. A top speed of 340 knots was reached during the flight, which lasted for 59 minutes. Following an uneventful landing, Schulk expressed satisfaction with the aircraft's stability and the way it handled. On the second flight, on May 4th, the A-12 went supersonic for the first time, reaching Mach 1.1. Problems were minimal, and Johnson began to feel confident that the flight test program would progress rapidly, possibly recovering some of the time that had been lost in the drawn-out manufacturing process. The Cuban Missile Crisis now reinvigorated the program. The loss of Major Rudolph Anderson's U-2 over Cuba on October 27th underscored the increasing vulnerability of this subsonic platform when operating in denied airspace, and this was not lost on intelligence community offices involved with the overflight program. At the end of 1962, two A-12s were in flight test, one powered by J-75s and the other powered by one J-75 and one J-58. A speed of Mach 2.16 and an altitude of 60,000 feet had been achieved. Flight test progress was still slow, and the engine delays and thrust deficiencies remained a major concern. Meanwhile, by the end of 1963, the CIA's A-12 flight test program had resulted in 573 flights, totaling 765 hours. 9 aircraft were on hand at the test location. It should be noted at this point that on July 24, 1964, President Johnson made the first official announcement concerning the forthcoming Lockheed SR-71. With the A-12 situation vacillated back and forth between an operational commitment and continued wait-and-see, flight testing of the YF-12A had continued. During July of 1966, Johnson wrote in the log, "We were directed to give up further flying of the YF-12As, although we had proposed shooting down a drone at Holloman to get the effect of ground clutter for low-altitude targets." The following August 5th, he wrote, "We've laid off half of our test crew on the YF-12A and are maintaining only enough people to store the airplane or send it to Burbank. We are very near the end of this program." As late as January 26, 1967, Johnson made the following comments in the A-12 log. "We jointly agreed there would be just one round and not two. That seems to have been a very accurate evaluation, as it seems that 30 SR-71s give us enough overflight reconnaissance capability, and we don't need the additional 10 A-12 aircraft." On January 5, 1968, an official wire closing down the F-12B was received from the Air Force. The YF-12A program would be formally ended on February 1st. In a final disheartening move, the Air Force, on February 5th, sent Johnson a letter instructing Lockheed to destroy the A-12 F-12 tooling. The final A-12 flight took place on June 21, 1968, when the last remaining aircraft, number 131, was ferried from the test location to Palmdale by CIA pilot Frank Murray and placed in storage. It would remain there for the following 2 decades. On June 24th, Johnson wrote, "While the intelligence community in Washington wanted very much to keep the A-12 program going, the present financial situation cannot stand the strain. It's a bleak end for a program that has been overall as successful as this." In summary, the A-12 program lasted just over 10 years from its inception during 1957 through its termination during 1968. The Skunk Works produced 15 A-12s and 3 YF-12As. 5 A-12s and 2 YF-12As were lost in accidents. 2 pilots were killed, and at least 6 had narrow escapes. In addition, 2 F-101 chase aircraft were lost with the Air Force pilots during the A-12 test program. The main objective of the program, to create a reconnaissance aircraft of unprecedented speed, range, and altitude, was triumphantly achieved. It may well be, however, that the most important aspects of the effort lay in its byproducts, the notable advances in aerodynamics, engine performance, cameras, electronic countermeasures, pilot life support systems, and the arcane art of milling, machining, and shaping titanium. Altogether, it was a pioneering accomplishment, almost certainly never to be repeated in the history of aviation. The YF-12A developed into the SR-71 And in that case, again, the cost performance was excellent, as we gave back to the government well over $19 million on the contract, and we consider it to be a success. On December 6, 1962, Kelly Johnson noted in his log, "Working on R-12 Universal Airplane using company work order. Can get no decision on any military version of the aircraft, but there does seem to be considerable interest in it." Johnson's rationale for this design was based on the premise that if he produced a single platform capable of performing the reconnaissance, recon strike, or intercept role depending on customer needs, it would greatly simplify production, and it eliminates the necessity of the Air Force deciding which version they want to buy. 7 days later, the Skunk Works was visited by several SAC personnel, and Johnson logged that they wanted to see what kind of a reconnaissance version would meet SAC's needs. We prepared our proposal for a 140,000-pound reconnaissance airplane capable of carrying 4,300 pounds of reconnaissance gear and gave it to Colonel Templeton with a forwarding letter. By March 18, 1964, R-12 construction was moving along with considerable rapidity, but contract negotiations had yet to be concluded with the Air Force. Johnson noted in the log, "Spent several days on the first 6 R-12s. It is extremely difficult to get a reasonable profit for what we do, and no credit is given for the fact we operate more cheaply than others. All activity relating to the R-12 and RS-12 configurations had, of course, been kept completely under wraps in the Skunk Works and within the confines of the involved Air Force and CIA offices." On July 24, 1964, however, President Johnson made his memorable announcement revealing to the world the existence of Lockheed's Mach 3-capable reconnaissance aircraft. "I would like to announce the successful development of a major new strategic manned aircraft system which will be employed by the Strategic Air Command. This system employs the new SR-71 aircraft and provides a long-range advanced strategic reconnaissance plane for military use, capable of worldwide reconnaissance for military operations. The Joint Chiefs of Staff, when reviewing the RS-70, emphasized the importance of the strategic reconnaissance mission. The aircraft will fly at more than 3 times the speed of sound. It will operate at altitudes in excess of 80,000 feet. It will use the most advanced observation equipment of all kinds in the world. The aircraft will provide the strategic forces of the United States with an outstanding long-range reconnaissance capability." In August 1964, Kelly Johnson phoned Bob Murphy and asked him if he wanted to work on the new reconnaissance aircraft. At the time, Murphy was a superintendent in charge of D-21 drone production. He accepted the offer and was immediately briefed by Johnson, who said, "I want you to go to Palmdale and get Site 2 away from Rockwell. Hire the people you need. The pieces of the aircraft will be up with you on November 1st, and I want her flying before Christmas." The SR-71 was 107 feet, 5 inches long, had a wingspan of 55 feet, 7 inches, and a wing area of 1,605 square feet. It stood 18 feet 6 inches high to the top of the rudders, and its gross weight varied from 135,000 pounds to over 140,000 pounds. The effect of thermodynamic heating brought about by the aircraft's extreme operating envelope was a major factor affecting its construction. Fully 93% of the airframe was built from titanium, while the remaining 7% consisted of laminates, of phenylsilane, silicone, asbestos, and fiberglass to help reduce the aircraft's RCS. The SR-71's forward fuselage has a circular cross-section and is of semi-monocoque construction. It housed the pilot and a reconnaissance system operator, RSO, seated in tandem, the front undercarriage, fuel cells, and the air refueling receptacle. The delta wing features 2 prominent engine nacelles, each mounted at mid-semispan and blended into the wing to further reduce RCS. Two rudders mounted on top of each nacelle and canted inboard 15 degrees from the vertical also reduced the aircraft's radar signature. A large aft-moving spike extends forward from each nacelle, which helped to regulate mass airflow to the two Pratt & Whitney J58 engines. The maximum fuel load weight for the SR-71 was 80,280 pounds, and it was carried in 6 fuel tanks. Built to cruise in afterburner at Mach 3.2 and at altitudes in excess of 80,000 feet, the aircraft encountered extremely high airframe temperatures generated by thermodynamic heating. This, coupled with the diverse operating envelope of its Pratt & Whitney J58 engines, required the development of a special fuel which served not only as the source of propulsive energy, but also as a hydraulic fluid optimized in the engine hydraulic system to activate the main and afterburner fuel nozzles. On the ground, the aircraft was only half filled with fuel, and then pressurized using LN2 to 1.5 psi above ambient pressure. Shortly after takeoff, the SR-71 would rendezvous with a tanker and get topped off. The Air Intel control system was a major innovation used to exponentially increase the speed performance of all Kelly-Johnson's so-called Blackbirds. At Mach 1.4, the outlet doors located in the exterior of the engine nacelle began to modulate automatically in order to obtain a prearranged ratio between dynamic pressure outside the inlet throat and static duct pressure inside the inlet cowl. At 30,000 feet, the inlet spikes unlocked and, at Mach 1.6, began moving rearward, achieving their fully aft position at Mach 3.2, design cruise speed. Cruising covertly during operational missions at speeds in excess of a mile every 2 seconds, it was essential that the SR-71's navigation system was both highly accurate and not reliant upon external navigation aids to ensure the aircraft remained on the black line. At the heart of successful mission accomplishment, therefore, was the Nortronics Astro-Inertial Navigation System, or ANS, designated NAS-142V2. Originally designed for the Douglas Skybolt air-to-surface ballistic missile, which was canceled in 1963, it proved to be a perfect solution for navigating the SR-71 after a few modifications and updates. The system combined data from the inertial navigation platform with a time datum accurate to within 5 milliseconds. Position updating was achieved automatically by astro-tracking at any one time 6 of the 52 most prominently visible stars by day or night, in effect using nature as a global positioning system long before GPS was developed. When the autopilot was coupled to the ANS via the auto-nav function, the SR-71 could be flown automatically, adhering precisely to a predetermined flight path that was loaded pre-flight into the ANS's computer memory. To facilitate maximum mission flexibility, the SR-71 featured 3 interchangeable nose sections, housing either a high-resolution, side-looking radar, used for ground mapping and referred to as CAPRI, standing for Capability Reconnaissance Radar, an advanced synthetic aperture radar system, or ASARS, or a so-called glass nose housing a palletized optical bar camera, or OBC. The SR-71 did not carry any form of defensive weaponry save that which was generated electronically. ECM was and remains a highly sensitive area, where fast-moving technological advances meant that the SR-71's defensive electronic systems required continual updating throughout its operational life. Within the SR-71's cockpit, pressurization was allowed to fall steadily as the aircraft climbed from sea level to 8,000 feet, whereupon it remained constant to 25,000 feet. This ensured that the fuselage wasn't subjected to unduly high pressure gradients, which in turn meant that the aircraft's structural weight could be reduced. However, if pressurization was lost or the crew needed to eject, survival was dependent upon each of them wearing a full pressure suit. This requirement was reinforced by Air Force Regulation 60-16, which stipulated that full pressure suits must be worn when flying above 50,000 feet. In 1977, the company developed the next generation of pressure suits, designated the S-1030 series, and featured a high level of commonality between the U-2 and SR-71 programs. Colored old gold, the suit incorporated state-of-the-art textiles and was more durable and comfortable. Its 4 principal layers consisted of an outer coverall of Nomex that was durable, tear, and fire-resistant. The helmet, designated GN121394, was attached to the suit via a rollerball ring to enable the head to be turned. Oxygen was supplied to the crew members through holes situated around the helmet face seal. An airtight port located on the lower right side of the helmet enabled crew members to drink water via a straw to ensure they remain hydrated, and a level of sustenance was also available in the form of liquidized food dispensed from a tube. Gloves completed the pressure seal and were attached via wrist hinges. Boots featured heel retraction strips that were connected by cable to the ejection seat on entry to the cockpit. The complete pressure suit system cost about $130,000 a copy. Crews were issued with 2, and they lasted 10 to 12 years, undergoing a complete strip-down overhaul every 5 years and a thorough inspection every 90 days, or 150 hours. December 22nd. The first SR-71, with Skunk Works test pilot Bob Gilliand at the controls, took to the air for the first time. Departing from Lockheed's Air Force Plant 42, Site 2 facility at Palmdale, it remained airborne for just over an hour and reached a speed in excess of 1,000 miles per hour, which, Johnson noted, is some kind of record for a first flight. Though the SR-71 first flight had been completed with few difficulties, ongoing flight testing of the aircraft had not been comparably problem-free. The SR-71 flight test program, conducted at Palmdale, like that of its A-12 predecessor, was not without its accidents. The first, involving the third SR-71A, occurred on January 25, 1966, when Skunk Works pilot Bill Weaver miraculously escaped without using his ejection seat. His back sealer, Jim Zwire, was not so lucky and was killed. At the time of the accident, the aircraft was in a right turn, and the right inlet forward bypass doors were being controlled manually by Weaver. Though SR-71s finally were beginning to enter the operational Air Force inventory, the miscellaneous subsystem problems remained difficult to overcome. Tank sealing and range deficiencies continued to plague the aircraft, including those considered operational at Beale Air Force Base, and corrective action was painfully slow in overcoming them. By late 1967, all 31 SR-71s on order from Lockheed had been completed and delivered. By late September of 1969, the SR-71 was well on its way to a long and illustrious operational career. SAC already had flown well over 100 hot missions out of Kadena. NASA, for the first time, formally inquired into having an SR-71 for test purposes on December 29, 1970, when a query was received by the Skunk Works concerning possible use of the aircraft to launch test-scale models of the forthcoming space shuttles. On July 28, 1971, Johnson noted in the log, "Nothing new on the SR-71 operation. SAC made a 10-hour flight a short time ago on which about half the time was over Mach 3 and 80,000 feet. They flew 10,000 miles. The Vietnam War had successfully justified the SR-71's existence from the time of its operational debut during 1968 through 1973. Some 600 missions had been logged during the course of Vietnam operations, and the aircraft had logged an enviable record of dependability and mission successes. Temporary deployment to forward operating locations, or FOLs, worldwide were undertaken with considerable alacrity, and during the course of its service career, the aircraft overflew almost every major political and military significant hotspot in the world, gathering intelligence data of inestimable political and military value. The previously mentioned YF-12A speed and altitude records were eclipsed by the SR-71A during a series of Fédération Aéronautique International monitored flights during 1976. As of this writing, all of these records still stand, including the world's absolute speed and sustained altitude records. During the late 1980s, as major international political and economic changes began to manifest themselves throughout the world, the U.S. intelligence community began to reassess priorities and, in particular, the way it was going to spend its limited financial resources. Virtually every program, including the SR-71, was reviewed with the intent of determining its long-term viability and, in particular, its simple cost-effectiveness. As a result of this review, and in light of advances in other sensor system programs, on October 1, 1989, all SR-71 activities, with the exception of crew proficiency training and associated training flights, were suspended while the Air Force awaited release of the 1990 fiscal year budget. When revealed several weeks later, funding for the SR-71 program had been eliminated. Accordingly, all Air Force SR-71 operations were terminated officially on November 22nd.
Good evening. Recent budgetary cuts for the Air Force have ended funding for the SR-71 Reconnaissance Aircraft Program. Local civilian and military personnel had the opportunity to view the final functional check flight of the SR-71 as it prepared to return to the United States.
Rolling down Kadeena's runway for one of the last times, the SR-71, nicknamed the Habu, performed a functional check flight in preparation for its last trip to the United States and into the pages of history. The atmosphere was charged with excitement as the flight crew, Major Jim Greenwood and Captain Steve Zaviniak, were assisted into 45 pounds of pressure suit. The physiological support technicians then conducted pressure tests on each suit and again performed these tests in the aircraft during pre-flight. The extra tests help ensure the suits will work in the event the pilots need to eject. The suits allow ejection at altitudes above 80,000 feet at speeds of Mach 3. After all pre-flight checks were done, the engines were started and the Habu came to life and soared into the skies of Okinawa for one of the last times. From Kadena Air Base, I'm Airman Rob Ivy.
Many of the Lockheed, Air Force, and CIA personnel who had been involved in the program during the preceding 24 years were on hand to say farewell to what many viewed as the single most significant military aircraft of the post-World War II period.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunk Works' Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth, and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the Dronescapes YouTube channel.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.